Welcome back, everybody. I hope everyone had a good little break. So any questions? A quick reminder, tomorrow you have the exam number 3. So just a reminder, give yourself plenty of time. Any questions about those chapters? If not, I'll be monitoring my emails tomorrow in case you do have a question. I'll monitor my emails to make sure I get back to you as soon as possible. Okay, well, we were in chapter 10, where we were talking about chemical reactions. Okay, let me refresh a little bit about that. And now there are only 6 types of chemical reactions that we're going to talk about. Okay, 6 types. So I'm going to go through each one in generic terms, in general terms. And then also going to briefly talk about how to balance these equations. Some of these equations, when we balance, they're simple enough that we can do a simple trial and error process. And that is adding coefficients to the reactant or the product, going back and forth as needed. And that is true for the first 2 we're going to talk about. With respect to the other types, we have specific suggestions on how to balance those chemical reactions. And recall, we balance them by putting coefficients in front of the reactants and products. And these coefficients tell us how many, let's say, reactants, in this case, A and B here in this example, are needed for them to react with each other properly and correctly. And sometimes it's a straightforward 1-to-1 ratio. I need 1A, 1B. Other times it could be a 1-to-2, 1-to-3 ratio, or even an off number, 2-to-3 or 4-to-5, whatever number it needs so it can react correctly, to assure that the number of atoms that you start off as reactants, you end up with the same number of atoms that end up as products, okay? And that's balancing. We're going to use those coefficients because those coefficients, we end up with a ratio, which brings us back to way back when in that chapter when we were converting units from, for example, we went from inches to centimeters, okay? We had a unit of 1 inch is equal to 2.54 centimeters. That was our conversion factor. Recall that we can write it in a ratio of centimeters on the numerator or inverted to have centimeters in the denominator. So that was a ratio. These coefficients are the same thing, okay? That's actually a ratio that we can utilize because eventually we're going to get to the point where we're going to calculate, if we start off with, let's say, X grams of A, calculate how many grams of AB in this example we create. Or alternatively, the question could be, all right, I need to make 10 grams of AB. How many grams of B do I need to start off with? Okay, so you can work those problems back and forth, but in order to do that correctly, we have to, first of all, write the reactions of the reactants and write the products. So we've done that. Remember, we talked about, we started with the atoms, and then from the atoms, we actually started with the ionic compounds. And we're able to put together, determine the ions of the elements that we were working with, as far as what charge they have. And that tells us how many anions and cations we need to put together. And that became the coefficient for the structure of that compound, the formula. So things like barium chloride, BaCl subscript 2, okay? Now what we're going to do is we made the compounds in the proper ratio. Now we're going to start reacting these compounds with each other to make new compounds, okay? And so we're kind of putting it all together. So eventually at the end, we can have a word problem where the reaction of sodium plus chloride gives you sodium chloride, for example. If I need to make 100 grams of sodium chloride, how many grams of sodium do I need to begin with? Okay, as an example. And we'll do some of those. All right. So anyway, before we get to that point, let's talk about the chemical reactions. There's 6 types. Okay. The first type is a combination reaction. Combination. So if you look at the, the definition of the word, it's straightforward. We have reactants that combine to create a new compound. Now, you will find that what combines are elements. So we have the elements over here, A and B, okay? And when they combine, they create a compound. Okay, so you start off with elements, whatever the case may be, whatever they are, and you end up with a compound. A classic example would be the reaction of hydrogen gas plus oxygen. Let me change this color a little bit, bring it up. It's not looking very clear from my end. And if I were to take the element hydrogen gas, react it with oxygen, another element, okay, diatomic, both of them, but nevertheless elements, they will react, I ignite it, and guess what I make? A compound, which is water, okay? So that's a classic example of a combination reaction. And so if you're given a reaction, they may ask you what type of reaction it is. Well, to recognize that it's a combination reaction, the criteria is the reactants have to be in elemental form, okay? And that will help you out to help classify that type of reaction, this type of reaction. Now, the opposite of the converse of a combination reaction is simply a decomposition reaction. In this case, you start off with a compound. In this example, you got A, B, C, and you do something to it chemically, you break it down, and you break it down back to the elements, okay? So a classic example again would be the electrolysis or the breaking down of water. The first one was a combination where we had hydrogen gas plus oxygen to give us water, okay? But a decomposition reaction could be taking water and then doing what we call an electrolysis. We break it down with electricity, and we break it back down to the elements. Okay, so the criteria for a decomposition reaction is that 1, you start off with a compound, and 2, the products you generate and create are the elements. Okay, the converse is true for a combination reaction. You start off with the elements and you create a compound. Okay, now with respect to balancing these 2 types of reactions, these type of reactions are fairly small and not very complicated. So we can utilize simply a trial and error process where you might say, okay, I got 1A here, but I need 2A. So I start putting numbers and coefficients and I go back and forth until everybody is balanced, okay? All right, the next type of reaction is a combustion reaction. We're all familiar with this. If you use your vehicle to go someplace today, your engine underwent a combustion reaction. A combustion reaction we're going to work with respect to Chem 130 is the combustion of what we call hydrocarbons. Okay, hydrocarbons. The definition of a hydrocarbon is a compound that is made up of nothing more than carbon and hydrogen, and that's it. Okay, carbon and hydrogen. Now, the subscripts X and Y, that just tells you how many carbons and how many hydrogens. The simplest hydrocarbon that there is a C1H4, FYI, for example. And this is called methane. We're all familiar with the term methane or heard it someplace. Another example of a hydrocarbon is if you use a lighter, okay, a butane lighter, flick your pick, that is butane gas in there, which is a hydrocarbon. And if you're gonna, do barbecue this coming weekend, You got the gas you're using, propane. Propane. In all cases, methane, butane, propane. Notice the A and E. The A and E depicts and classifies it as a hydrocarbon. There's nothing but carbon and hydrogen. Now, one of the requirements for any combustion obviously is oxygen. Okay. So if you don't have oxygen, nothing's going to burn, but it's required. Now, with respect to Chem 130, okay, the combustion of hydrocarbons, okay, leads to only two products. Number one, carbon dioxide, and number two, water. Yes, I'm well aware that your vehicle, for example, which when you burn your gasoline, there's a variety of hydrocarbons in there. One of the gases that emit is carbon monoxide, a poisonous gas. But that's simply because of the inefficiency of our engine to operate properly and to combust the hydrocarbons efficiently and correctly. And so, yes, there's carbon monoxide being formed there, but we're not going to talk about all the products that you could get for Chem 130. The combustion of a hydrocarbon yields two products, carbon dioxide and water. Okay. Now, with respect to balancing a combustion reaction, we have a step process. Okay, and I'll give you an examples here in a bit. But step number one, we balance the carbons first for the combustion of hydrocarbons. After we balance the carbons first, we then balance the hydrogens. Okay, and then once we're done with the hydrogens, we then balance the oxygens, and by adding coefficients. And I'll give an example of how we do that. The takeaway here is that you should be aware that if it is worded, if the problem is given to you in words and say, okay, write the products, maybe for example like this, I don't know, say write the combustion reaction of C6H6, okay? That could be potentially a question, okay? Well, C6H6, you may not know what it is, and that's okay, okay? That's all right. But I hope you recognize that C6H6 is nothing more than a hydrocarbon because it's made up of nothing but carbon and hydrogen, okay? So point number one. The keyword combustion tells you that oxygen has to be involved with respect to the combustion of this C6H6. So I can start writing the reaction, C6H6 plus oxygen, okay, will react to give me the only two products that are generated from the combustion of a hydrocarbon, and that is carbon dioxide and water. Okay, so now you have written the reaction for the combustion of C6H6. Not knowing what C6H6 is, that's okay, but you do recognize that it is a hydrocarbon. And you also recognize that it's a combustion of hydrocarbons, so oxygen is required. And then finally, you recognize that the only products generated are carbon dioxide and water. Okay, excuse me. So at this point, then you will balance it, and we'll go through the steps to balance it, but we won't do that here. We'll have a slide there to balance these type of reactions. Okay, that's a combustion reaction. Second one, we had a whole chapter on acids and bases. Remember, by definition, and most of the time we're dealing with the Arrhenius definition. The Brownstedt-Lowry definition, if you move up in the Chem 151, 152, that may come into play a little bit more. But for us, we're going to stick mostly with Arrhenius definition of an acid and a base. So if you recall, An acid is one, first of all, it is a covalent compound. Okay, A is a nonmetal, H is a nonmetal. So things like, give an example, hydrochloric acid. Okay, recall I mentioned that one of the difference between an ionic compound and a covalent compound is that when you take an ionic compound and you dissolve it in water, it will dissociate in water. Some of the ionic compounds dissociate 100%, therefore they are a strong electrolyte. Some of them, depending on the solubility rules, dissociate much, much less and therefore are classified as insoluble. Okay, but nevertheless, they do dissociate in a variety of different amounts, depending on what type of ionic compound it is. With respect to covalent compounds, when you place them in water, they do not dissociate. They remain intact and therefore are non-conductors. The only exception I mentioned was acids. Okay, they have that property of when they dissolve in water, they will generate, in this case, hydrochloric acid, would generate HCl, the proton. Okay. Now, with respect to a base, notice this. Bases are those species that, when dissolved in water, generate the hydroxide polyatomic ion. And if you look at the general formula, it is an ionic compound because it's a combination of a metal and a nonmetal. Okay, so we have a covalent compound, acid, in the presence of an ionic compound, base. And when that goes in solution, that base produces the hydroxide ion, which defines it as an arrhenius base because it generates the hydroxide ion. When the proton and the hydroxide combine, okay, they produce a molecule of water. It's a neutralization reaction. The proton, which is the acid, gets neutralized by the base. Now, the takeaway from this is the following. It's a 1-to-1 ratio. One proton requires one hydroxide to give me one molecule of water. If I have 10 to the 6 proton ions, I need 10 to the 6 hydroxide ions, which will give me 10 to the 6 molecules of water, okay? So if I have 1 billion protons, I need 1 billion hydroxides, and it will give me 1 billion waters, okay? And I state that because when it comes to balancing an acid-base reaction, my suggestion is follow the proton and the hydroxide. Follow those, get those balanced, and the rest just falls in place. And we'll have a few examples of that. Okay, but first recognize that you are dealing with an acid. And I did mention this before. 99% of the time, you'll see hydrogen written first, followed by some other non-metal material. Okay, and hydrogen in general is written first. It's a good indication that it is a acid. Okay, and then with respect to the base, be able to recognize the OH, the hydroxide. All right, so neutralization reaction / acid-base reaction. Okay, the second type, the fifth type, it is called a single replacement reaction. Now, let's analyze the general reaction here, okay? We have a metal labeled M in elemental form. It's in the elemental form. It's not combined with anything else. In the presence of an ionic compound, which consists of a metal A and some nonmetal X, notice that? You are dealing with two metals. One is in an elemental form, and the other metal is in ionic form, okay? Now, if there's a reaction that precedes, the metals exchange places. And so now where you had the metal A that was in ionic form, now it becomes in elemental form. Elemental form. And the M, which started off in elemental form, now is combined to go into ionic form. Now, the driving force is this. If this reaction is written as is written here, this implies that the metal M, whatever that metal is a lot more stable in ionic form than it is in elemental form, okay? And we'll repeat that. If this reaction proceeds as written, the new product, which the new metal now is in ionic form, it is a lot more stable in ionic form than it was in elemental form. And that is why this reaction proceeds. Now, how are we going to determine that? I'm glad you asked. All right, because if we go to the periodic table, okay, and right above the solubility rules, you will find what is labeled as an activity series, okay? That activity series is a listing of metals and their reactivity relative to each other and relative to hydrogen gas, okay? Because if we look at this, you'll see that hydrogen, oh, let me change my, if we look at hydrogen, hydrogen's right here, okay? Now, on the first 1, 2, 3, 4, 5, 6, the first 6 metals there are written in bold print and underscored. What that tells you is those metals are extremely reactive, and that in the presence of, simply in the presence of water, they react with water immediately and quite violently, actually. So if we were to take sodium metal and pour it into a bucket of water, it would just react violently with the water, generate hydrogen gas and give off a lot of heat and actually ignite the hydrogen and give you a nice little bang, okay? Okay, I have more to say on this in a second. Now, if we look at the other metals, starting with magnesium, right, so after sodium, and proceed all the way up to lead, notice they are not in bold print, okay? They're just regular print. Those metals are not as reactive as the ones that are underlined, okay? And therefore, they will survive in ordinary water. They will not react with water by itself. But they do require a little more vigorous conditions. So starting from magnesium all the way up to lead, in order to get those guys to react, we need to add like an acid solution, like a hydrochloric acid, making the solution more acidic. Then you get a reaction, okay? And then finally, after hydrogen, you have copper, silver, mercury, and the last metal, Au, which is gold. Gold is the least reactive metal there is, okay? That's why we call it the noble metal, because like the noble gases, they're very unreactive, and it takes extremely vigorous conditions to get gold to react. Okay, but by itself, that's why gold that was buried, 1,000 years ago, when it gets pulled up, and it's just as shiny than it was the day it got dumped in the ground, because it's so unreactive. Okay, copper, silver, mercury, and gold, very unreactive, even under acid conditions. They will not react. They require very vigorous acid conditions for them to react. Okay. Now, the way you read this table is as follows. Let me zoom it up a little bit more. You'll see the symbol greater than. So what that tells you is lithium is the most reactive metal there is. Okay. And it is more reactive than potassium, which is more reactive than barium, strontium, calcium. Sodium is more reactive than magnesium. and so on and so forth until we get to the end of the list, and we get to go, okay? And that's how you read that. Now, we utilize it to determine whether a reaction we're given will proceed. And the driving force here is you ask yourself two questions. I shouldn't have said driving force, but the question is asked is this. Of the two metals that you look at, be it as an elemental form or be it in an ionic form, of the two metals in the process, in the reaction, which metal is more reactive? So you use the activity series to determine that. Once you determine which one is more reactive, then the next question asked is the most reactive metal in ionic form? Okay. If that answer is yes, the most reactive metal is in ionic form, it's stable, no reaction, nothing's gonna happen. If the answer is no, that is that the most reactive metal of the two you're comparing is not in ionic form, then reaction proceeds, okay? Reaction proceeds, and like I stated, we will do some examples, okay? So in this example here, we looked at the table, and in general terms, we found that M is a lot more reactive than A, the metals. We're just looking at the metals, okay? That's step one. Step two, is M ionic? Okay, and it's not, because M is in element form. So if the answer is no, then reaction proceeds as written. Positive reaction, okay, as follows. And you simply just flip the metals with each other, and before you put the new ionic compounds together, you write them in ionic form so you can make sure they come together in the right ratio, okay? All right. Again, we'll do some specific examples here. I gave it to you here in generic terms. And the last one here is called a double replacement, okay? Now, what drives this reaction, if there is a reaction, is the solubility rules. This is the driving force with respect to the product. Now, if you look at the metals, we got two different metals, and they're denoted by subscript 1 and 2. And it's not saying there's two metals there, it's just saying that two different metals, okay? It would have been better to label it M and A, for example. All right, now, both of the reactants are in ionic format. They're in ionic compounds, okay? Furthermore, if you look at the solubility rules for the reactants, you'll find them to be soluble. So M1X and M2Y are in aqueous solutions. And normally they're nice and clear, colorless solutions, not always, but they are. And then maybe I have two test tubes of them, and they're separated and they're nice and clear. Now what happens is I mix them together, and they're gonna exchange partners. So MX now becomes MY, okay? And M2Y now becomes M2X, okay? So you just simply exchange the partners. They're ions, they're interacting with each other, you know, just by chance, the new partnership comes together. And now, what determines if any reaction here is the solubility rules. If both of the new products are insoluble, okay, you get NR, no reaction, because they're still in solution, nothing's happening. If one of the products is soluble, excuse me, I stated that backwards. Let me restate that. Okay. If both of the new products are soluble, okay, then you get no reaction. Nothing happened. Okay, they just exchange partners and they go back to the original partners back and forth, and that's it. Now, if they're classified as one of the reactants, one of the products is classified as insoluble based on the solubility rules, then a reaction proceeded. And you denote this, but let's just say for argument's sake that M2X is insoluble, we put the letter S, okay? And then that's a positive reaction. Only if one of the products or both of the products are insoluble. Okay, so we rely on the solubility rules for this. This is very similar to the one we did. Remember this one before we left? Okay, where we had the two ionic compounds, which was nickel 3 sulfate and lead 2 nitrate. They were both soluble, denoted by the AQ, okay? They exchanged partners, so now it became nickel nitrate, which is right here. We look up the solubility rules, nickel nitrate is soluble, it's AQ, so we write AQ. We look at the other partnership, which is lead sulfate, lead 2 sulfate. Guess what? Based on the solubility rules, it is insoluble. And so we get a positive reaction, okay? So this is a positive reaction, RXN for short-handed for reaction, because one of the products was insoluble based on the solubility rules. Now, to balance these type of reactions, follow the polyatomic ions. And I did talk about this when we did this last slide here, but follow the polyatomic ions here to help you balance out these reactions. The cations will just fall in place automatically, okay? Okay, for single replacement reactions, it's like a combination and decomposition reactions. They're pretty simple, straightforward. You can utilize utilize a trial and error process to get those balanced. Okay. For balancing the acid base, I don't know if I mentioned that. Follow the protons and the hydroxides. That would balance your waters, and again, the anions that come with them will just fall in place automatically. Okay, any questions so far? Okay. Well, here's an example of a combination reaction. It could be given to you in words. It could be said, phosphorus in the presence of oxygen yields diphosphorus tetroxide. Okay, that could be written out, and then you take the words written out and you backtrack and you write the formula. Okay. All right. Notice something. Phosphorus is elemental form. Oxygen is the elemental form of oxygen. They combine to form a compound. A compound, by definition, consists of two or more different elements. Here we got phosphorus and oxygen. Okay, so that is a means to determine and to classify what type of reaction this is. All right, so we have the reaction here, and now what we got to do, we got to balance it. Now, most of the time, trial and error, but I could suggest when you have elements that are all by themselves, monoatomic, I would suggest leaving them alone. Don't try to balance those right away. That will help you out later on by putting a coefficient here and get things balanced. I would start with the diatomic and then balance the oxygens first, okay? It's a suggestion. You don't have to do that. I can put a 2 right here and balance my oxygens, and then put a 2 here and then balance my oxygens, okay? But you'll find that in this case, that works out okay. Sometimes it doesn't, so I recommend leave the monatomic ion elements alone and work on the other. So we got 2 oxygens on the left, 4 on the right. We simply put a 2 in front of oxygen. That balance out our oxygens, right? We got 4 O2s, 4 O2s. Now we got two phosphorus on the right, we need a 2 on the left, and we simply put a 2 there. And now double check, I got 2 phosphorus on the right, 2 on the left, 4 oxygens on the left, 4 on the right. We are balanced. This is a balanced chemical reaction. And note the ratio of reactants, okay? And so it's a 2 to 2. So I could, if needed, write that relationship between reactants as follows. Or I can invert it and do it this way, because it depends on the question being asked, which we're going to work with down the road, okay? And remember, when we're being asked a question, the question is normally going to say, well, what we're looking for unit-wise will always be in the numerator. What we're trying to get rid of unit-wise will be in the denominator, because we're going to be multiplying this first factor maybe by, I don't know, 5 oxygens. Wanted to know how many phosphorus we need, something to that result. Now, I'm sure you recognize that 2 over 2 is a 1-to-1, right? If you recognize that, that's fine. But until you do that and you're comfortable with that, bring the coefficients over, okay? You'll see mathematically that 2 divided by 2 is 1. And so in this scenario here, I would need 5 phosphorus for every 5 oxygens, because it's a 1-to-1 relationship. Okay. Okay, now here's an example of a decomposition reaction. Iron 3 oxide, aka rust. Iron 3 oxide will break down to generate iron and oxygen. Okay. Another way to make oxygen out in space, we find some iron 3 oxide, we can decompose it and generate oxygen. And then we take the iron and add a little carbon to it and make steel. All right, so note the relationship here. We have a compound. We break it down to the elements of iron and oxygen, okay? Decomposition reaction. All right, well, we got to balance it. Now, like the time that we were putting together, when we're putting together the compounds, like, I don't know, let's say we had sodium and chloride, the ions. Well, we know it's a 1-to-1 relationship. To the right, the formula for sodium chloride is simply NaCl. And then things like, I don't know, calcium chloride. We know that the chlorides each have a negative. We need 2 of them. So our formula was calcium Cl subscript 2. When we got dissimilar charges, let's say calcium and nitride, recall that in order to put them together properly with the right amount of negative and positive charges, we had to find a common number, okay? And the common number here was 6. So we needed 3 calcium plus 2s and 2 nitrites, because we ended up with -6 total and +6 total, and all that equals to 0, okay? So those numbers in front of the ions became the coefficient. So the formula for calcium nitride was Ca subscript 3 and subscript 2. Okay, recall that? Okay, well, we can use that same technique here, finding a common factor when we're trying to balance it, okay? Recall what I said about the elements that by themselves. Save that for last. Work on the oxygens. Leave that single guy by himself. You'll find a lot of times it works out perfectly, or you just put a coefficient there and you're done. But in the meantime, try the oxygen. Now, with oxygen, I got 2 on the right and I got 3 on the left. Okay, so we have a dissimilar number like we did with calcium nitride. So we find a common number, right? So if I put 2 in front of iron 3 oxide and 3 in front of oxygen, guess what? My oxygens get balanced, because now I got 6 oxygens on the left and 6 on the right. So they're balanced. What that does is that kicks up my total number of ions to 4. Okay, now, having left the iron alone there, I can simply put a 4 in front. And guess what? Now my irons are balanced. Okay, so I require 2 iron 3 oxides will give me 4 irons and 3 molecules of oxygen. Okay. And again, keeping track of the relationship between reactants and products. The relationship here is 2 iron 2 oxides for every 4 irons. Okay, 2 to 4, or isn't that a 1 to 2, right? Then this relationship over here, or I can invert it to make the other one, but I got the other relationship, 2 iron 3 oxides to 3 oxygens. It's another relationship, or I can invert it. Okay, the same is true here. Invert it, depending on what I'm trying to calculate. All right. Now, here's the question. This is write the combustion reaction of propane gas. So this coming weekend, you're cooking up that hamburger on your propane grill. You are burning up 3 carbons and 8 hydrogens. You know, keep that in mind. Okay. All right. So first of all, let's write the reaction. So we're given to us C3H8. This, by the way, is the 3-dimensional model of propane. The dark spheres represent carbon, and then the white represent the hydrogen. Okay, and all 3 of them have the tetrahedral configuration. Okay, and a lot of these hydrocarbons can be very long chain, 8, 10, 12 long chains. A lot of the fatty acids, those of you, keep track of your fatty acids, are very long chain hydrocarbons, 10 to 12 chain of carbons. And then on one end, you have an acidic part, an acid part, like acetic acid has. And anyway, they have a fatty acid part, which is the hydrocarbon part. And then they have a polar part that's soluble in water, which is the acid part. All right, so we write the formula C3H8, and we know it's a combustion, right? Combustion means that I need oxygen. Okay, no oxygen, no burning, plain and simple. And recall, we are dealing with a hydrocarbon. It's a molecule made up of nothing but carbon and hydrogen. And so the only 2 products we generate are carbon dioxide plus water. Okay, and they're burning, so everybody's in the gas phase. I'm not going to put the physical state, but yeah, when it's burning, carbon dioxide is a gas, the water is the gas, you vaporized it, oxygen's a gas, and they're telling you propane is a gas. It definitely is. Okay, it feels like a liquid because it's in the pressure tank, but you open that tank up and it goes away as a gas. All right, now, when it comes to a combustion reaction, we have a step process to balance it. Number 1, we first balance the carbon, okay? And so we have 3 carbons over here on the left, 3 carbons over here. I need to balance the carbons on the right, so I simply put a 3 in front of carbon dioxide. So that balances my carbons. So carbon's okay. Second, we balance the hydrogens, okay? Well, we look to the reactant side. We got 8 hydrogens in the reactant side. We go over to the, this is 3 carbon over here. We go to the product side, there's only 2 hydrogens, and we need 8, okay? So we simply put a 4 in front of H2O. Okay, because every molecule of water has 2 hydrogens. So we just need 4 molecules of H2O to give us 8 hydrogens. Okay. Notice how we're going back and forth. We start off as a reactant, then we go over to the, start off as a product to balance, then go back to the reactant side. Now we go back to the product side. We go back and forth, okay? Now, finally, we balance the oxygens. And so we got 2 O2s on the left-hand side, but on the right-hand side, we got 6 coming from carbon dioxide and 4 coming from water. So we got a total of 10 oxygens on the product side, 6 in carbon dioxide and 4 in water, a total of 10. Okay, so we're going to come over here, and normally you have a number that is divisible. Once you count all your oxygens on the reactant side, that number should be divisible by 2. So I take that 10, divide by 2, and I put a 5 there, right? Because I only need 5 molecules of oxygen gas because they're diatomic. All right, so even though I got 5 molecules of oxygen, each one carries 2 oxygen, a total of 10. Okay, so now, ladies and gentlemen, we have a balanced chemical equation. Okay, let me clear up my mess and put down balanced chemical equation. Notice, observe something. It takes for every molecule of propane, you need 5 molecules of oxygen to burn, to combust, to get rid of all the propane. Okay. And so, you know, if I need 100 molecules, if I have 100 molecules of propane, I need 500 molecules of oxygen. The ratio is 1 to 5 to get rid of that propane. Furthermore, it generates 3 molecules of carbon dioxide and 4 molecules of water, okay, plus a lot of energy, which is a good thing, right? Because without that energy, you can't cook your hot dogs. All right, a lot of energy given up. So 4 molecules of water, 3 molecules of carbon dioxide, which the water and the water vapor and the carbon dioxide eventually get into the atmosphere and can cause a potential problem. All right, now, this is pretty straightforward when you have an even number of a number divisible by 2 as far as oxygens. But occasionally it doesn't work that way. Occasionally you end up with odd numbers, okay? Well, let me do an example of in case you run into, like over here, remember we had 10 oxygens. We counted 10 oxygens here total on the product side. Well, we simply put a 5 there and we're good to go. You know, if you had a 20, if you ended up with 20, all right, no big deal. I'll put a 10 here and good to go, all right? Occasionally you end up with an odd number of oxygens. And then you have to take one more step. And I'm going to do an example of that. Oh, somebody had a question. Sorry, just saw it. Diesel fuel, again, diesel fuels are hydrocarbons, okay? Now, keep in mind, a lot of the fuel that we use are formulations. So they're not a pure hydrocarbons. They got all kinds of other components in there for a variety of reasons, you know, make things burn, you know, some of them have alcohol, you know, in the fuel, you know, alcohol is in there, it's an alcohol, it's not a hydrocarbon. So, yeah, by and large, majority are made up of hydrocarbons, is made up of hydrogen and carbon. Most of them are larger molecular weight, bigger size. Okay, does that answer your questions there? Okay, got it. All right. Either way, all of them, gas and gasoline and diesel eventually create carbon dioxide and water. A lot of it, actually. Okay, so let's do an example of an hydrocarbon where you end up with an odd number of oxygens. And the question is, well, how do I balance that out? Okay, so I'm going to give you this generic formula, which is, oh, hold on. C, oh, clear this. C6H14, okay. Now, there's 6 carbons here, and the prefix for 6 is hex. Now, there are, if you can imagine, there's a different, I can take those 6 carbon and put them in different configurations, and we have a number of different compounds that contain 6 carbons. Those are called isomers. That's beyond the scope of what we're doing, but just be aware that it is 6 carbons and 14 hydrogens, and it's a hydrocarbon. Okay, so we're going to combust it. Now, obviously we need oxygen, right? It's a combustion of C6H14, a hydrocarbon, so oxygen is required. And then our products are like the case we just did with propane or butane or any hydrocarbon, is we generate carbon dioxide and water. Okay? All right. So given this formula, which, you know, any hydrocarbon, we could have said C100H, whatever number it is, same process. It's a combustion. You're going to need oxygen. You're going to create carbon dioxide and water. All right. Remember, step number 1, we deal with the carbons first. So we got 6 carbons over here. So we're going to add a 6 over here. That balances the carbons on the right side. Okay. Number 2, we balance the hydrogens. Well, we got 14 hydrogens on the reactant side. Well, to balance that, notice that water, I need 7 molecules, water molecules, to give me 14 hydrogens. Okay, so I put a 7 in front of water. And then finally, number 3, I balance the oxygens. Well, obviously I only got 2 oxygens over here. But on the right side, I have 12 oxygens coming from carbon dioxide, right? Plus 7 coming from water. So that gives me a total of 19 oxygens. 19 oxygens. But I got 2 on the left side. So I got an odd number, right? If that would have been 20, then no problem. I just throw a 10 in front of O2 and I'm good to go. But I got a 19. So what you do on a temporary basis, we work with fractions. And so I just need, I need 19 molecules of oxygen, but I only need half of them, right? Because every molecule of oxygen, you know, there's 2 oxygens. So I need 19 of them, but only half of them. So I can very temporarily add 19 over 2, 19 halves, okay? Keep in mind, the coefficients for any chemical reaction should always end up in whole numbers, okay? But you can temporarily use fractions of half to get to the point where you want to get to, okay, to balance it out. All right. So we want to get rid of the half, the 2 of 19 and a half. And so like any fraction, if I want to get rid of, you know, I got 5 halves, I want to get rid of the 2. What do? I multiply by 2, do I not? Right? 2, the 2's cancel out, I end up with 5. And so what I do is I take this whole thing and I multiply everybody by 2. So it's understood to be a 1 there. Okay, so it's 2 times this. 2 times 19 halves gives me 19. 2 times 6 gives me 12. And 2 times 7, right, gives me 14. All right, so let me clear up a little bit. So and remember, this is only for cases where you end up with an odd number of oxygens on the right-hand side. It will help you balance it out. So 2 times the C6H14 says I need 2 of these C6H14 molecules, okay? 2 times 19 is 19 oxygens. Okay, 2 times 6 is 12 carbon dioxides, and 2 times 7 is 14. Okay, now you might say, remember, we want to have numbers that we can reduce the lowest terms. These numbers are reduced to the lowest terms. Okay, 19, especially when you got an odd number, I can't reduce that any further. That's it. So those are the coefficients. Now let's double check to make sure that everybody's still balanced. I have 12 carbons on the left-hand side, and guess what? I got 12 on the right side. Okay, I got 28 hydrogens, and guess what? I got 28 hydrogens on the right side. Okay. So how about oxygens? How many oxygens do I have on the left-hand side? What's 19 times 2? Isn't that 38? 38 O2s, oxygens on the left side. Okay. Now on the right side, I got 24 oxygens coming from carbon dioxide, plus 14 coming from the water. Isn't that 38 oxygens? So everybody checks off, and we have a balanced chemical equation. Okay. So for this particular hydrocarbon, I need, first of all, I need 2 molecules of the C6H14 and 19 molecules of oxygen to yield 12 molecules of carbon dioxide and 14 molecules of water. Okay. And these are fairly small hydrocarbons, so you can see the trend. We start off with propane, okay, and we didn't need that much oxygen, but as we start increasing in the size of a hydrocarbon, the trend is we're going to need a lot more oxygen, and it's going to generate a lot more carbon dioxide and water. Okay. All right, so that's what we do with respect to balancing a chemical reaction of a hydrocarbon. You start with a carbon, hydrogen, and then oxygen. Okay, and then if you end up with an odd number of oxygens on the right-hand side, then you just use this technique we just used to get everything balanced. Okay, because you don't, when you're done balancing your chemical reaction, you end up with whole numbers, not fractional numbers. All right. And this information is basically what I just stated, that balancing tip, carbon, hydrogen, then oxygen. And we know that the products are always carbon dioxide and water, and the reactant, obviously, besides the hydrocarbon, is oxygen. Okay, well, in this scenario, we're looking at examples of the chemical reactions. So we have an acid-base neutralization reaction. We call, in general terms, we have the proton reacting with the hydroxide to give us water, and then the corresponding salt, which is the metal from the hydroxide, combining with the non-metal of the acid. Okay. So a salt does not necessarily mean just sodium chloride. A salt is an ionic compound. And that metal can be anything other than sodium. It could be potassium, any of the metals. And A is normally a non-metal, most of the time the chlorides, okay, or the phosphates, or anything of the sort, whatever was the anion of the acid. Okay, well, here we have specific reactions. We see that we have HCl, which I hope you recognize by now, that is hydrochloric acid, and you have the formula for barium hydroxide. Barium hydroxide. So you can see that we're dealing with a base and we're dealing with an acid. All right. Now, barium hydroxide has a hydroxide in parentheses with 2, which tells you there are 2 hydroxides that will be generated for every barium hydroxide. Okay? Which means that you need 2 protons. Remember, we're neutralizing this. So if I have 10,000 hydroxides, guess what? I need 10,000 protons to neutralize it. Okay? I'm given here, I have 2 hydroxides. So that means I need 2 protons. And I simply put a 2 in front of HCl to give me 2 protons. Well, what that means is I'm going to create 2 waters, right? Again, if I have 1,000,000 protons, I need 1,000,000 hydroxides. And when they combine, I'm going to get 1,000,000 waters. And so here I have 2 protons, 2 hydroxides. I'm going to create 2 waters. So guess what? My hydroxides and my oxygens are balanced here, okay? What's left now is the ions. So before I do anything, I'm going to write them out in ionic form so I can combine them carefully. Barium is a +2 ion, okay? And the chlorides that are created are a -1 ions, okay? To put these together, I need 2 chlorides for every barium. So the formula becomes BaCl2, okay? Now I go back and check. My bariums cancel out, are balanced, and my 2 chlorides are balanced, and there's my formula, okay? And that is my reaction. So in this scenario, to balance acid-base reactions, follow the protons and the hydroxides. Get those balanced right away, and then everything else falls into place. Before you put the salt together, put them in ionic form first, so you can know how many of each you need to put together. Okay. All right. Let's do one more, the second one. Now, instead of barium hydroxide, we have another base here. We have calcium hydroxide. Okay, it could be magnesium hydroxide. All right, now we have an acid here. How do we know it's an acid? Well, first of all, we got hydrogen written first. Then second, we got PO4, which if you look at the polyatomic ion, that comes from the phosphate ion. And in order for that phosphate ion to be generated, it actually came from phosphoric acid and reacted with the base. Now, on the left side, I got 3 protons, and on the right side, I got 2 hydroxides. I have a disparity, right? And I want to react it such that everybody gets neutralized. Well, how do I do that? Well, as we were doing before when writing formulas and balancing, when you have a disparity of numbers like this, 3 to 2, what do? You find a common number. In this case, 2 and 3, the common number is 6. So if I put a 2 right here, that will give me 6 protons, all right? And if I put a 3 in front of calcium hydroxide, guess what that does? That gives me 6 hydroxide ions. So I got 6 protons, 6 hydroxides. Guess what? I'm going to make 6 waters. Okay, like I said earlier, 1,000,000 protons, 1,000,000,000 protons. I need 1,000,000,000 hydroxides to neutralize each other, which will create 1,000,000,000 molecules of water. Okay, now, as in the previous case, I had the salt to put up, but before we put them together, we write them in the form of ions. Phosphate has a PO4 -3, and then the calcium has a +2, okay? And so in this case, in order to put these together, we have another disparity again, where we got a -3 and a +2, we're going to put them together such that they cancel each other out with respect to the ion charges. And so that means I need 3 calcium to give me the common number of 6 positives. And I need 2 phosphates to give me a total of -6 charge for the phosphate. So the formula becomes Ca3 parentheses PO4 lowercase 2 subscript 2. Okay. And so now we go back and check. We know the hydrogens and the oxygens are good to go because we went through that scenario. The phosphates, we got 2 of them over here, and we got 2 over here on the product side. We got 3 calcium on the reactant side, and we got 3 calcium. So by default, if I put them together in the right ratio, they balance each other out. Okay. So let me clear up my mess, and we'll bring in the slides. Okay, so we got 2 there to balance out the hydroxide, which creates 2 waters and 1 barium chloride. Remember to write the salts in salt form first. Okay, we look for a common number here, which was 6. So it gives 6 protons on the left, 6 hydroxides on the right. Okay, we end up with 6 waters and the formula C calcium phosphate. Okay. Any questions right now up to this point? So with respect to acid-base reactions or neutralization reactions, follow the protons and the hydroxides to get a balance. Okay. All right, so now we get to the single replacement reactions. Okay. This is where we start off with an elemental metal, denoted here by the letter M, and then a metal which is in ionic form. Okay, and if there's a reaction, the metals change position, and now where we had metal element, now we have ionic metal M, which was elemental form, now becomes in ionic form. Okay, and then the A, which was in ionic form, now is in elemental form. A classic example of this is plating. Okay, I don't know if you're familiar with plating or not, but you know, you got gold plating, chrome plating, copper plating. You can literally plate all kinds of metals. Okay, and generally you start off with a solution with that metal that you want plated on some surface. It's an ionic form dissolved in the solution. Then you react it, do something to it, you convert it to an elemental form, but you convert it back to elemental form on some surface so you can plate it with whatever you want to do, what you want to do as far as the type of plating. All right, so what drives this is 2 things. One, the activity series, okay, which is the listing of the metals that are relatively reactive to each other. Okay, which one's more reactive? And the driving force is this, that if we look at this general reaction, what it should tell you is this, that the metal in elemental form, in the presence of another metal in ionic form, that metal is not in a stable state. It is a lot more stable in ionic form than it is in the elemental form, but only when it's in the presence of a less reactive metal in ionic form. Okay, that's the bottom line. That's what it amounts to. Okay, the M is a lot more stable when it's ionic in the presence of another metal that is ionic. All right. So let's get to know about the activity series. I talked about it. The ones in white are the ones that are very reactive. They react with water. So what I'm going to do is for these metals, I'm going to very generically call them M prime, okay? So M prime metals, that's lithium through sodium, in the presence of water, okay? M prime in the presence of water react violently, very, very quickly, and they produce hydrogen gas. Plus, they produce the metal prime hydroxide. Okay, and so they took some hydrogen off of the water and regenerated the hydrogen back into elemental form hydrogen, and then it made the metal hydroxide. So in this case, if we were to take some recall in the acid-base chapter, we talked about litmus paper. If we were to take a red litmus paper and we put it in that solution after everything's said and done, it would change that red litmus paper to blue. And that's because it would generate a base in this process, okay? Now, the other metals, starting from magnesium up to lead, I'm going to call those M double prime, okay? So the M double prime in the presence of water, no reaction. Okay, no reaction. It takes a lot more vigorous conditions. So what happens is those metal primes, I'm gonna write it down here in the bottom, metal double prime, if I reacted with an acid solution, which I'm gonna designate in generic terms HA, okay, guess what happens? I get hydrogen gas, starts to bubble, plus the metal double prime salt, whatever that A was, okay? A lot of times it's hydrochloric, like so metal chloride, but it could be others and besides the chloride. So, and that is only for the metals of magnesium up to lead. They require a little more vigorous conditions, and that is the general reaction for those particular metals. You generate hydrogen gas, and you get the salt and hydrogen gas, okay? And then that means that, notice H. H is the hydrogen, which could be in the form of either a proton or water, as far as ionic form is concerned. The most, well, I'll do that in an example in a bit. So the other metals from copper on up to iron, like I stated, if you were doing like hydrochloric acid, no reaction, or plain water, no reaction, it really requires some stronger acid to get those metals to react, because they're very relatively unreactive, okay? All right. And so the lithium is the most reactive metal, and it goes down the road until we get to gold, which is the least reactive metal, all right? Magnesium is a lot more reactive than zinc, okay? Barium is a lot more reactive than calcium. See how that works? And iron is a lot more reactive, let's say, than cadmium, cobalt, nickel, tin, or lead. All right, so the steps in looking at these type of reactions. One, we check the activity series to find out which metal or hydrogen is more active, okay? So the most active wants to be in compound form. If it's already in the compound form, then there's no reaction, okay? Let me repeat that. When you are comparing the two metals or hydrogen, depends on the reaction, the one that is most reactive, if the one that is the most reactive is already in compound form, then we get no reaction NR, and there's no switching the partners, okay? If it's not in compound form, that is the most reactive metal or hydrogen, then you get a reaction and we essentially switch the partners. And when we do that, you got to make sure that we write the new compound in ionic form first, so we make sure we put them together in the proper ratio. Okay, and of course you gotta recall your physical state. Okay, balance the equations and so forth. Well, let's take a look at this one. We have zinc nitrate, aqueous zinc nitrate, in the presence of sodium metal. So step number one, we got to find the metals, okay, regardless of whether they are in elemental form or in compound form. We're just comparing the metals. We got zinc there and sodium right there. So number one says that sodium is a lot more reactive than zinc, okay? Number two, sodium, is it a compound? Is the question. The most reactive metal is the most reactive metal in compound form, okay, based on the reaction. Here, it says no, because it's an elemental form, which implies that yes for reaction. And now what we do is we switch partners. So zinc, which is in compound form, goes into elemental form, okay? And now sodium goes into ionic form. So we first write the ion. We know that sodium has a +1 charge. And we know that the nitrates, based on the polyatomic ion table, each have a -1 charge, okay? So we got a positive for sodium, a negative for the nitrate. We can simply put them together as a 1-to-1, okay? That takes care of that. That's the formula for sodium nitrate. Now, to balance these guys, I would follow the polyatomic ion ions. We got 2 nitrates on the left. If I simply put 2 nitrates on the right, that balances out my nitrates. Okay, my zincs are okay, no problem there. I got 2 sodium now by putting the 2 there, so I just simply come back and put a 2 in front of sodium, and it's balanced. Let me clear it up a little bit. Okay. Of course, we're not going to use the formula Na, then nitrates in parentheses 2. That implies that sodium is a group 2 element, you know. It's not. It's a group 1A element and only has 1 valence electron. So it could not be the formula. It could not be the formula Na parentheses subscript 2 for the nitrates. All right. All right. Let's do this. Let's take a quick 15-minute break. I got 11:19. Why don't we come back at 11:35? Yeah, 1:35, excuse me, 11:35. 1:35, let's come back in 15 minutes and we'll continue, okay? Be right back. Okay, we're back. And so looking at the single replacement reactions, again, you use the activity series to determine which metal is the most reactive, regardless of what state it begins as, whether it's in ionic form already or in elemental form. And so here we're comparing sodium and zinc. Okay, we find them on the activity series. Here's sodium, and here's zinc. This tells us that sodium is a lot more reactive. Sodium is more reactive than zinc. And then we ask, is the most reactive metal, which in this case is sodium, is it in a compound form? In this case, it's not. It's an elemental form, so therefore reaction proceeds. You simply exchange the partners, okay? So zinc automatically goes to its elemental form. So in this case, we're basically plating, if you will, removing zinc, or this is one way to get pure zinc out of a solution, if that is what you're striving to do. And then the sodium then partners up with the nitrate. The nitrate, nothing happens to the nitrate. They're spectators. There's what we call spectator ions. They're there to counter the positive charge. Nothing happens to them. So the new ionic compounds, write them out in ions form first, so you can put them together properly. And then once you're done with that, for these type of reactions, if you have a lot of polyatomic ions, follow the polyatomic ions to help you balance the chemical reaction. Okay. And obviously this can't be true because we know that sodium is a +2 ion. It's in group 1A. And that would infer that sodium would be in group 2A, and that's not the case. Okay. Any questions at this point? All right. Now, here we have another one. And so we have aluminum in the presence of strontium bromide. And the question is, would this reaction proceed? Well, we need to first find the elements on the activity series, and there's strontium, and there is aluminum. And so strontium is more reactive than aluminum. Okay. And is strontium in compound form? Okay. And the answer to that is yes. Okay, because it is strontium bromide. Therefore, that implies NR, no reaction for this particular chemical equation written. No reaction because strontium bromide. Strontium is a lot more reactive than aluminum, and the most reactive metal is already in compound form. Okay, so what this also tells you is, guess what? The reverse would be a positive reaction. What do I mean by that? Well, instead of starting with aluminum elemental aluminum, we start off with aluminum in a compound form. And so we have here strontium, which should be a solid, plus let's call this aluminum bromide. And the question is, would that reaction proceed? And you go through the same process. We know that strontium is a lot more reactive than aluminum, okay? And second of all, strontium written here in equation number 2, this is the first one. It is not in an elemental form, so a reaction proceeds. Okay, so this means that aluminum bromide now becomes aluminum solid, and then strontium, which is a +2, and the bromides, which are -1. We need 2 of those, so we got SR, Br2. Okay, aqueous, and that would be the reaction for the opposite reaction. Okay, all right. Okay, now here we have aluminum and hydrochloric acid. Okay, now keep in mind that the activity series is what's the word I'm looking for? Is relative to the hydrogen. Okay. And if you look at the activity series, here's hydrogen here. Hydrogen is right here, okay? So taking a look at aluminum and hydrogen, we go to the periodic table, excuse me, we go to the activity series, there is aluminum and there's hydrogen. So aluminum is more reactive than hydrogen, okay? All right, now, question is the most reactive metal in ionic form in this reaction? The answer is no, it's not, okay? It is not. Now, hydrogen gas, that's the elemental form. The ionic form of hydrogen is H+, the proton, okay? And so right now, hydrogen is in the proton form or ionic compound, but it is not as reactive as aluminum. So we have to exchange places here. So we're going to exchange the aluminum, and the hydrogen are going to exchange, which means that the hydrogen, which is in ionic form, now goes to elemental form, which is H2 gas, okay? Aluminum, we write it first in ionic form. We know it's a group 3 element, so it will be a +3 ion. And the chlorides each are -1. So we need 3 of them. So the correct formula for aluminum chloride is Al, okay, Cl3. Okay, see how that works? And this is consistent with the reaction. Remember that all the metals from magnesium up to lead in the presence of an acid will give you, remember I used that general M double prime, would give you the M chloride, M halide, whatever it would be, the M anion plus hydrogen. And that's what's happening here, okay, in this reaction. The metal becomes the M, the salt, and then the hydrogen becomes the elemental form. Back to the elemental form. Okay, so that is the formula, and then obviously we got to put the put it into the physical states. Okay, and now we could balance them out, and you end up with 2 aluminums per 6 hydrochloric acids. You generate 2 aluminum chlorides and 6 molecules of hydrogen gas. Okay. Now there are YouTube videos already pre-made on the module that I gave you for this particular chapter. So do review those if you get more information. Okay. Dr. Kim does a very good job in her explanation. So it gives you an alternative approach of presenting this information. And finally, to kind of summarize as far as these reactions using the activity series is: 1, you determine which is the most reactive metal. Ask the question, is it in salt form / compound form? If it says yes, if it is, then no reaction. Okay, if it's not in compound or salt form, then there is a reaction. Now keep in mind that if there's no reaction, what that implies is the opposite reaction is feasible. Okay. All right, now with respect to double replacement reactions, we had a single replacement reaction. Here we have a double replacement reaction. This is analogous to the one we did just before we finished up last time we met before break, where we had 2 compounds that were soluble in water. We mixed together, they exchange partners, and one of them is insoluble based on the solubility rules, and therefore reaction occurred. Okay, and so if we look at AX, for example, it's an aqueous solution based on the solubility rules, it's soluble. And so when it breaks apart, it's going to create the ions A and X, whatever the charge it may be, A positive, X negative, whichever. As far as the amount, the quantity, I don't know, because these are generic examples. So the BY is also aqueous and soluble in water. And they also dissolve into the ions, and then they have a partner change. So the AX becomes AY, and the BY becomes BX. Now, based on the solubility rules, BX is soluble, okay? So it stays in solution. On the other hand, the new compound that was created based on the solubility rules is classified as insoluble. And therefore, in this example, this general example of a double replacement reaction, AY is insoluble. Therefore, this reaction is positive, okay? If AY was soluble, AQ, then there would be no reaction, okay? No reaction. All right, so let's do a couple examples, okay? Yeah, we talked about this before, where these solid materials called a precipitate. That's a rehash of what I just stated. All right, so learn or be familiar with the solubility rules. And what we're going to do is kind of rehash everything. Okay, I'm going to rehash a little bit more. I think we talked about this, but maybe not in earnest, not in detail. So let's do that. Okay, this is in the periodic table on the right side. Now you have two columns. You got the left column, which is the soluble column, okay? All right, with respect to the soluble column, number one, if you have these four cations, lithium ion, sodium ion, potassium ion, and ammonium ion, whatever it is combined with, whatever anion it's combined with, it is soluble, always 100% of the time. So anytime you see sodium, potassium, ammonium, or lithium up front, and then followed by whatever, and you want to determine whether it's soluble or not, you don't have to go any further. Those four guys, I call those the big four, those four cations are always soluble, okay? So it'll be labeled as AQ. Number two, this is the acetate anion, okay? The majority of what we're going to follow through have to do with the anion. The cations are the only ones there are the ones in number one. So the acetate anion, that comes from acetic acid that's been treated with base to form the acetate anion. Okay. The negative charge polyatomic ion. Whatever positive cation is attached to, it is soluble. Copper acetate, lead acetate, any metal acetate, it is soluble, okay? The same is true for number three, the nitrate. Any metal nitrate, it is 100% soluble all the time, hence we can label it as AQ. All right, now there are some exceptions, and here's the first exception. Number four, the halides, group 7, the bromine, the chloride, the bromide, and the iodide. Any metal halide that those three are attached to normally are 100% soluble, except, and repeat, except when those halides are bonded to silver, mercury, or lead, okay? So any metal, copper, bromide, copper halide, any copper halide, any sodium halide, obviously sodium, but any metal halide other than those three heavy metals, silver, mercury, and lead, are soluble except those three, which are classified as insoluble, and therefore we will put the S, okay? Number 5, very similar to number 4. We're talking about the sulfate ion. The sulfate ion, any metal that the sulfate is attached to is soluble in an aqueous solution, with the exception of these 5. Calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, and lead sulfate are classified as insoluble, okay, in the aqueous solution. And so there's like thousands of other metal sulfates that are soluble, except the calcium, strontium, barium, silver, and lead. Okay. All right. Now, with respect to the column on the right, this is the insoluble. Okay. For number 6, 7, and 8. Okay. The carbonated ion, the chromate ion, and the phosphate ion are, regardless of what metal they are bonded to, are insoluble, except if they happen to be bonded to the big four. Okay? And so for the carbonated ion, there's only 4 examples of it being soluble: lithium, sodium, potassium, ammonium carbonate. Okay, so, and the same is true for the chromate and the phosphate. Only 4 examples for each one, which are classified as soluble, and everything else in the world it's bonded to metal-wise, it is insoluble. Everything except those four are soluble. Okay, number 9. Very similar. Normally, the sulfite ions are insoluble, regardless of what metal it's attached to, what cation, okay, except the 4 that are there: lithium, the big 4, lithium, sodium, potassium, and ammonium. And on top of that, 3 more. If the sulfite is bonded to calcium, strontium, and barium, and 4, so there's only 7 examples of sulfide compounds that are soluble, and that everything else out there that we know to date are classified as insoluble. Okay, they form a precipitate when you put them in water. For the hydroxides, same thing. Okay, unless they're bonded to the big 4 and calcium, strontium, and barium. So there's only 7 examples of hydroxide compounds that are soluble, and everybody else it's bonded to are insoluble. In my life as a research scientist, we use quite a bit of iron and copper in our process, and we needed a way to remove copper and iron from these 5,000-gallon tanks of this iron solution. And before we can dump it in the drain or anything, we had to clean up all that iron. So we would treat it with a hydroxide, sodium hydroxide. And when they combined with the hydroxide combined with the copper and the ion, they form a precipitate, and it will precipitate out. And we run it through this big old filter press, and that will get rid of all of the iron and all the copper, plus a lot of other trace metals, such that that when we would analyze the water before we put it down the drain, that water with respect to metals was a lot cleaner in Overland Park, Kansas, than the water coming into the tap. So our water going out the tap is much cleaner. Okay, so that's how the solubility rules work. And you got a solubility column. There's some exceptions that are compounds are not soluble, that they are classified as insoluble. And the same is true for the insoluble column on the right. Okay. So let's take a look at this reaction here. The first thing that should tell you, possibly if you're doing the double replacement, is that both of the reactants are in aqueous solution. Okay, so that's a good suggestion that you might be working with a double replacement. Plus the fact that, you know what, you're also dealing with polyatomic ions. Okay, so that's a good indication that possibly you're dealing with a double replacement reaction. All right, now what I want to do here first is I'm going to go ahead and break them up into ions, okay? So and the reason I want to do that is I want to put them together again after they exchange partners in the correct ratio, okay? And so by breaking them up, I know how many, first of all, I know how many ions I have of each, and then I can put them together in the correct ratio when they rearrange the cell. So I'm going to take barium nitrate and break it up into the ions. I know that barium has a +2 charge. It's a group 2A element, plus the fact that the nitrates are -1 each, and there's 2 of them. So that infers that the barium is a +2. And so we have 2 nitrates, each with a -1, okay? Now the magnesium, again, is a group 2 element. It's a M+2, all right, ion, and the sulfate is a SO4 -2. Okay, so those are the reactants. When they put in solutions, they separate into the ions. Now what happens is they exchange partners. So the barium now partners up with the sulfate, okay, and the nitrate partners up with the magnesium. Okay. Now, when I combine the barium and the sulfate, note that I get a +2 for the barium and a -2 for the sulfate. So I can put them together on a simple 1-to-1 ratio. Okay, so we're going to come back to the solubility here in a second. Now, the other aspect is the magnesium and the nitrate. Well, the magnesium is a +2, okay? And the nitrates are a -1, but there's 2 of them already for you. So you know what? I'm going to bring that 2 along. Obviously, I have to, right? Because magnesium is a +2. All right, now, so I broke them into ions, and then we put them together again with the new partners, the new anions and new cations. The next step is determine solubility. All right, nitrates. Nitrates, if you look on first column, number 3, nitrates, regardless of what the nitrates are bonded to, they are 100% soluble. So magnesium nitrate, it is soluble. I can put AQ, okay? Barium sulfate. Well, barium sulfate, I got to look for the sulfate, which is number 5. Okay. Normally, sulfate ions, regardless of what the metal is soluble, but there are 5 exceptions, of which one of them, barium sulfate, is insoluble. So that means that this new barium sulfate is insoluble, and I put an S there. What that tells you is that this reaction is positive because the new product, barium sulfate, is insoluble. Okay, and so that's our new products. Now we got to balance it, and I think by default, because we broke them up into the ions, that they are balanced automatically. So let's double check. I got 1 barium, 1 barium. I got 2 nitrates. Guess what? 2 nitrates. 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. By default, they just balanced out. Okay. That one worked out okay. So definitely have a positive reaction here. And reaction just by default. Breaking them into ions really helps to make sure that things get balanced out properly. Okay. All right, and these are polyatomic ions. Don't separate them into the atoms. You just keep them together. All right, let's do the same thing. Another one. We have lead nitrate. Now, question is what is the charge of lead? Well, what do we know about the nitrates? Each one's a -1, right? And there's 2 of them. That infers that lead has to be a +2. okay? And then we have 2 nitrates. Then we have potassium, which is a +1, it's a group 1 element, and iodide, which is a -1, okay? So those, there they are, all in ionic form. Now we exchange the partners, so lead gets partnered up with the iodide, and the potassium gets partnered up with the new partner with the nitrate. Okay, lead has a +2 charge. That means we need 2 iodides. So our products here will be lead subscript iodide subscript 2. Okay. Then we have potassium and 2 nitrates. Okay, so potassium is a +1, the nitrate's a -1, so we can put them together as potassium nitrate, as follows. All right, let's check the solubility. Recall nitrates, number 3, regardless of what they're bonded with, all of them, 100% of the time, they are soluble. We got AQ, okay? Iodide, which are the halogens, number 4, normally the halogens are soluble, except when they're bonded to the heavy metals there of silver, mercury, and lead. Okay, it's bonded to lead. So that means that lead acetate, lead 2 iodide is insoluble, so it's a solid. Okay. All right. Now, in the beginning, we saw here that we had 2 nitrates to begin with because we had a 2 right here. So when I put nitrate here together, I could put a potassium nitrate together. I can put a 2 there because I do have 2 nitrates that came from the lead nitrate. So I got to put a 2 there. And what that does is that kicks up my potassium to 2. So I simply put a 2 right there in front of Ki. And now everybody is balanced. I got 1 lead, 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides. We are balanced. Okay. All right. Now let's do, I think let's do one last one. Barium chloride, we got Ba +2, and the chlorides are all -1. There's 2 of them, okay? We got silver, which is always a +1, but we also know that nitrates are always a -1, so that infers that silver has to be a +1, okay? All right, so let's exchange partners. The silver and the barium nitrate combined. Okay, so barium nitrate, it's a +2. Each nitrate is a -1, so we need 2 of them. So we got barium and 2 nitrates. Okay, and then the silver chloride, it's a +1 and -1, so it's very simple. AlCl, silver chloride. Okay, let's look at solubility. All nitrates, okay, number 3, all nitrates are soluble. So this is barium nitrate, always soluble, okay. The halide, number 4, the chloride is sitting there. It is bonded with silver, therefore it makes it insoluble. So silver chloride is insoluble, we got an S, therefore its physical state. All right, now, we need to balance things. So we got the barium chloride. So we had 2 chlorides here. So we got to balance the 2. So silver chloride put a 2 right there. Okay. And by putting a 2 on the chlorides and silver chloride, it kicks up my silver to 2. So I need to go back and put a 2 in front of silver nitrate, which again kicks the nitrate up to 2. Well, that's okay because I got 2 nitrates there from in barium chloride, nitrate. So it balances itself out. Okay. Okay. Again, with respect to double replacement reactions, if both new products are soluble, we get no reaction. Okay. If one of them is insoluble, or even both of them are insoluble, then you have a positive reaction. Okay, which brings me to this general classification of reactions. They're called redox reactions, and it's short for two words: reduction and oxidation. And a lot of the reactions that we just did can be classified as what we call a redox reaction. Okay, now what exactly does that mean? Well, reduction and oxidation. Reduction is what we call gain of electrons. When a metal, like we did the single replacement reaction, when a metal gains electrons, it goes into, becomes an element, okay? That gain of electron is called reduction, okay? When, and I say a metal, when because that's the majority of the time, when something, I should put in generic terms, when a compound gains electrons, we call that reduction. When a compound loses electrons, we call that oxidation. Okay, and if you look at the RED and the OX combined gives you redox. Okay, the thing about redox reactions, they occur together. You cannot have a reduction happening all by itself and an oxidation happening by themselves. And they're the yin and the yang of chemical reactions. There's a redox reaction occurring right now in the battery that you're utilizing if you're running off the battery. On one end of the battery, the chemicals there are gaining the electrons, and the other end of the battery, it is losing electrons, and the batteries are being transported from point A to point B, and then your equipment utilizes those electrons to operate whatever equipment you're operating, okay? That's a battery, and that's your equipment. It uses electrons to visualize on your computer, be it a computer or whichever you're using, iPad or cell phone, okay? So redox reactions is simply the loss or the gain of electrons. Now, what happens is, with respect to reduction, the element's charge, whatever charge it is, be it zero, be it plus, be it negative, it goes down, okay? And so, let's say, using, I'll come back to that for a second. In oxidation, the element charge goes up, its oxidation number goes up. And so it's analogous to a scale. I don't know why they make it kind of complicated sounding here. We got 0, and then we got positive 1, 2, 3, all positive, right? And if you go down the scale, those are -1, -2, -3. And so let's say you are at 0. And electrons, lose their negative charge, correct? And so if you lose electrons, now your oxidation state, your number becomes positive. So your number goes up from 0 to +1. That's what they're saying right here. Oxidation, it goes up, okay? Whereas reduction, let's say you're at 0 and you pick up an electron, Now you become a negative charge. Down here, you go down the scale. And so your charge overall goes down with respect to value magnitude, because positive is a higher number than the negative number in that sense. So that's what they're trying to tell you here. Bottom line is this: you're going to either lose or gain electrons, and you're going to lose negativity or gain negativity. And if you lose negativity, you become positive, right? And if you gain negativity, you become more negative. It's all what it amounts to. Okay. They occur simultaneously. Now we talk about the charge of elements, but we should be using the term oxidation number. Okay. It's the same as the charge, but the oxidation number is more really describes the situation a little better, because with respect to metals and nonmetals and ionic compounds specifically, they end up with a full positive and a full negative charge. Okay, remember that? If it's a metal, loses electrons, you get a full positive, or if it's a nonmetal, it's a full negative charge. So yeah, right there we can talk about your charge. But when we talk about covalent compounds, we don't have a full charge. We talked about partial charges, we call that, where because of the electronegativity, the electrons are sharing a bond, and when the electronegativity of one of the elements is stronger, it pulls the electrons toward itself much stronger, leaving one area with a partial positive and another area with a more of a negative area, a negative charge, okay? So, but it's not a true charge, it's just electron density. And so we really can't call it a charge, so because it's kind of ambiguous, so we use the term oxidation number. And unfortunately, I kind of tend to bounce back and forth. I try to maintain, be consistent, and talk about oxidation number. But keep that in mind when we're talking about the charge of that element, whatever it may be, okay? Elements in their natural state are normally zero because they have an equal number of protons and electrons, right? We know that group 1 metals, 1A metals, when they become ions, they lose an electron and they become a positive 1. Group 2A becomes positive 2. Group 3A are metals, become positive 3, okay? The group 4, starting with carbon, it can be anything because they're on the fence. They had the capability of either losing 4 electrons or guess what? Gaining 4 electrons. Remember, the driving force here is to lose electrons prior to group 4, is to lose electrons so that now they're isoelectronic with the noble gas behind it. And after group 4, the goal there is to gain electrons so they become isoelectronic with the gas, noble gas in front of it, meaning that now they have the same number of electrons, okay? And the octet has been fulfilled. Group 4, they're on the wheel, they're on the fence, I should say. And depends on the reaction conditions, they can either gain 4 electrons because they have room for 4, or they can lose those 4 electrons. So their oxidation state can vary from a -4 to a +4. Depends on the conditions. After that, starting with group 5 and forward, they're all nonmetals. They're getting closer to the noble gases, and all they got to do is pick up 2, 3, or 1 electron to get that octet fulfilled. So group 5 will pick up 3, group 6 picks up 2, group 7 picks up 1. And obviously the noble gases are inert. Their octets were fulfilled and they're not going to do anything. So I had the periodic table that showed you that everybody in group 1 and group 2 had a constant and exact oxidation number, okay? And then I gave you 4 more, which included the zinc, cadmium, and silver, and aluminum. They had exact oxidation numbers. So there was the sweet 16, right? That meant that we don't need to use Roman numerals to describe their charge. We just call it what it is because we know what they are. It is all the other metals that we needed to use Roman numerals to to determine your charge, okay? So losing electrons under oxidation, the charge goes up, okay? And like that scale I showed you, start at 0, you lose electron, your value now, let's say you lose 1 electron, now you go to a positive number. You're at 0, you go up to a positive 1. An example of that would be copper, element of copper shown here, in which it loses 2 electrons. This is an oxidation of copper, losing 2 electrons. So solid copper is what is being oxidized. When you identify who is being oxidized, then it also has a second name. It has another name, I shouldn't say second, it has an additional name, being that species that lost the electrons is now classified or named the reducing agent. Why? Because they are the ones that give up the electrons for somebody else to pick them up. Okay, sort of like a ticket agent. You know, ticket agent's got the tickets for you to buy your tickets, right? So copper here is the reducing agent because it's offering up its electrons for somebody to use someplace somewhere. Okay. Reduction is the gain of electrons, and therefore the charge or oxidation number drops. So if you're at 0, for example, and you gain electrons now, let's say you gain 1, now you are at -1. So that's, in that sense, the charge drops down with respect to their value, right, to -1. Sulfur picks up 2 electrons and it becomes sulfide, okay? So in this case, solid sulfur is reduced, okay? And it is classified as the reducing agent, oxidizing agent, pardon me, because it is the species that pick up the electrons that the reducing agent, whoever it may be, let go of. Okay, remember, redox, one cannot occur without the other. They occur simultaneously. Okay. So what is oxidized and what is reduced? They are always the reactants. The products they are what they are. They didn't have nothing to do with it. Their products didn't do anything other than become what the products are. It's the reactants that either gain or lost electrons, okay? All right, so if you're asked the question, well, which compound was reduced? Well, you got to name the whole compound, not just the metal themselves or the non-metal that pick up electrons. So if copper chloride is involved in picking up electrons, and it's copper chloride, for example, not just copper. Okay, for example, we have this reaction where we have copper 2 in the presence of iron, reacts to give you the copper metal and iron 2. Okay, so copper 2 went from a +2 oxidation number to a 0 oxidation number. Okay, and so in order to go from a +2 to 0, it must pick up 2 negative values, 2 electrons. Okay, so it was reduced. Whereas iron went from a 0 to a +2. Well, to go from a 0 to a +2, you must lose 2 electrons. Okay, so iron was oxidized because it went from a 0 to a +2. So what was oxidized is iron solid. What was reduced was the copper 2 ion in this case. If that copper 2 was bonded to anion, then we would name the whole compound. But right now they're just showing the ion. So the copper 2 ion is what was reduced. Therefore, the copper 2 ion is the oxidizing agent, and the reducing agent is the iron. Okay. All right, here's a real life example of the making of a particular compound. Some of this some of these compounds that are created are actually used in the treatment of cancers, so the platinum compounds. So here, if you take cobalt nitrate, okay, in the presence of platinum, you get now platinum 3 nitrate and cobalt. Okay, and so here, cobalt went from a +3 state. Now, how do we know that's the case? Well, let's break it down. Okay, we know that every nitrate has a -1 charge, right? Every nitrate has a -1 charge. So we got 3 nitrates bonded around the cobalt. Well, if that's the case, then this cobalt has to be a +3. Isn't it not? This is in the +3 oxidation state when it's combined with 3 nitrates. When it comes over here, solid, it is in the 0 state because it gained 3 electrons. You see how that works? Now, platinum starts off in a 0 state. And when it becomes platinum 3 nitrate, as the case of cobalt, the nitrates each are a -3, -1. Okay, so that implies, like we did with cobalt, that this platinum has to be a +3 stage. Okay, so it went from a 0 to a +3. So that individual gained electrons. Okay, lost electrons. What am I saying? Let me clear the mess up here a little bit. Okay, so what is oxidized is the platinum because it went from 0 to a +3. Oxidation is the loss of electrons, okay? Loss of electrons. So platinum lost 3 electrons, and cobalt nitrate, cobalt 3 nitrate is what was reduced. So cobalt picked up 3 electrons, okay? Therefore, cobalt 3 nitrate is the oxidizing agent, and platinum is the reducing agent. All right. Of course, that's the name for, we use the Roman numerals, okay, because these metals are not part of are not a member of the sweet 16, so to speak, right? And the 16, we know those are exact oxidation numbers and therefore do not require Roman numerals. It is all the other metals that have variable oxidation number, and therefore we have to distinguish them by utilizing the Roman numerals. All right, take some time. Not only this video, I will upload it, but take some time and look at the other videos and so forth. Bear with me 1 second. stand back. Sorry about that. Anyway, as I was saying, we do have videos. Dr. Kim has made these. They're in your module with respect to this particular chapter. So take a few minutes if you can and listen to her perspective on this chapter. Okay, so to summarize this whole chapter, be familiar with the solubility rules and how to utilize them. Okay, be familiar with the activity series so you can determine whether a reaction whether a reaction will proceed as written based on the activity, reaction activity of the metals. Okay, be able to recognize and balance combination reactions. Balancing for these combination reactions are pretty simple, so it's basically going to be like a little trial and error. Okay, same is true for the decomposition reactions. Okay, how to recognize them. Remember, a combination reaction, it is the coming together of two elements to create a compound, whereas the decomposition reaction is the process of a compound being broken down back into their elements. Okay. Recognize, write the products, and balance single replacement reaction. The single replacement reactions deals with the activity series. If the most reactive metal, based on the activity series, is in compound form, then there's no reaction. Okay. If the most reactive metal is not in compound form, then there is a reaction, and you simply just replace the position of the metals. As far as the ion compounds, remember to write those as ions first so you can put them back together with the correct ratio. Okay. The double replacement reactions, those are governed by the solubility rules. If the new products, and all they do here is you start off with two reactants that are both soluble and you combine them. The partners exchange, they get new partners, so to speak, if you will. And then depending on the solubility of the new partners, if the new compound generated is insoluble, then you got a positive reaction. If the new products are both, or all of them are soluble, then there's no reaction occurring. Okay. Acid-base reaction, that is the reaction of a proton and a hydroxide ion to give you water. You're neutralizing the acid and the base. Okay. To balance these reactions, follow the protons and follow the hydroxides. And remember that if I have 10 million protons, I need 10 million hydroxides to give me 10 million waters. All right, in combustion, in our case, the only thing we're going to combust are hydrocarbons, and these are carbons that are made up of nothing but carbon and hydrogen. Right. Second of all, we balance these combustion reactions by first balancing the carbon, followed by the hydrogen, and then at the end you balance the oxygen. If you end up with an odd number of oxygens on the reactant side, no problem. Just use that fractional method that we utilize to help you write the correct balanced chemical reaction. Okay. And then be able to identify from a reaction, okay, what was oxidized, what was reduced, okay? What metal, what species compound gained electrons and which ones lost the electrons. All right, with that being said, congratulations, you are now done with chapter 10. And given that we have only 9 minutes left, I think I will continue with chapter 11 next week. We'll definitely do 11 and 12 next week because 11 has about, chapter 10 is about, I want to say 10 slides, if even, very short, okay? All right, well, let me pause it here.